Hi everybody, my name is Kale-ab Tessera, and I'm going to speak about learning compact, general-purpose neural network architectures. This is the work that I'm doing at the University of Witwatersrand with Benjamin Rosman. So the main difference between neural architecture search and standard deep learning is that not only are we optimizing the weights, but we're also trying to learn the architectures. Slides look a bit bad. I think this is on Publisher, but the main reason why we want to learn the weights is because in deep learning, we spend a lot of time focusing on optimizing the weights, but we don't spend enough time on focusing on the function, which is represented by the architecture. We don't spend a lot of time focusing on the specific functional form. If we started with the architecture and then optimized the weights, we should be able to get better results. So neural architecture search has kind of three components. The first one is the search space, which is what architectures is it possible for me to find. The second component is the search strategy. How am I going to choose a specific architecture? And examples of search strategies are random search, Bayesian optimization, evolutionary methods. And then the third part of neural architecture search is performance estimation. How am I going to estimate how good this architecture is that I've chosen? An easy way of doing this is looking at the test accuracy or looking at the test loss, but obviously this is quite computationally expensive. The main problems with the current approaches in the field is that they're quite computationally expensive and they have millions of parameters. And another thing is that they have a very restrictive search space. Majority of the neural architecture search methods focus on convolutions and learning convolutional layers. And the problem with that is convolutions rely on your data having some sort of structural information and structural importance. If this isn't the case, then convolutions don't work very well. So when we say compact, we mean we're trying to learn smaller models with fewer parameters. When we say general purpose, it means we're not using anything specific to any domain. So no convolutions, no residual layers, no skip connections. We're just learning neurons, we're learning connections, we're learning hidden layers. The first thing we started doing is investigating the similarities between dense and sparse neural networks. A dense neural network is what you guys are all familiar with. It's a feed-forward, fully connected network. A sparse network just has some of the weights that aren't active. We compared dense and sparse neural networks, and we said if we have a dense network and if we have a sparse neural network, and we give them the same amount of weights, how do they behave? Do they give us similar performance? And we found that dense and sparse neural networks give us similar performance when we give them the same amount of weights. And we increased the amount of weights and we saw that they behave similarly when we look at their accuracy and when we look at their loss. Another hypothesis that we investigated is maybe if we have less data, then maybe dense neural networks would perform better than sparse neural networks. And we found this not to be the case. So even with 10% of the data, dense and sparse neural networks give us similar performance when we're working, in this case it was on MNIST, with one hidden layer. So we wanted to investigate this further and see, do dense and sparse neural networks behave similarly when we have more hidden layers? And we found out that it does. So when we increased it from one hidden layer all the way up until 32 hidden layers, we found out that dense and sparse neural networks behave similarly when you give them the same amount of connections or your weights. And so this led us to believe that what's more important is your number of weights, which relate to the capacity of a neural network. And this led to our work on learning sparse neural network architectures. So essentially, we have this parameter called density, which is the percentage of hidden layers, or percentage of active weights in a hidden layer. And what we can do with the search space is we can learn these architectures. And we found that we actually get good performance, but I think an important component of this is that we actually use less active weights. So on MNIST, we're able to get around 97.86% accuracy with only 60,000 active weights, which is equivalent to having one hidden layer with about 50 nodes. So if you have any more questions, you can speak to me at this poster session, poster number 16. Thanks.